Thank you. So I will show you a new method for detecting and monitoring atmospheric natural hazards with GPS radio occultations, which means detecting and monitoring tropical cyclones, convective systems, and volcanic eruptions. So a brief introduction about the GPS radio occultations and how it works. There is a satellite, GPS satellite, sending a signal. When the signal crosses the atmospheres, is banded and received by another satellite, which is LEO satellite. And measuring this banding here, we can also measure the atmospheric parameters. In this case, we can measure the first product coming from the GPS is the banding angle, which can be transformed in the refractivity and then temperature, pressure, and water vapor. So the measurement of GPS is GPS phase and amplitude. From this, we can get the banding angle. Through the Abel inversion, we get the refractivity. And through this equation, from the refractivity, using the ECMWF model, we can retrieve the temperature, pressure, and water vapor. So we can profile all the atmosphere by using such kind of signal. There are a few missions ongoing now using GPS radio occultations. This is the number of occultations from 2001 to 2013. At the beginning, from 2001 to 2006, there were just 2 missions working and acquiring just a few hundred radio occultations a day. But then in 2006, there was a new network called Cosmic, which is an American network of GPS receiver. And this is the reason, because there is a big increase in 2006. And this is still working. In 2006, it will be launched a new network, a US network, Cosmic 2, and the number of occultations will definitely increase. And here you can see the distribution of the occultations that we have used for this work. You see that the density of radio occultations within the tropics is the lowest, and then there is an increase of density at about 20 degrees south and north, and about 50 degrees. So the pros and cons of the GPS radio occultation technique, the pros are high vertical resolution, starting from 60 meters in the lower troposphere. Global coverage, high accuracy, long-term stability is a cheap technology because it uses GPS antenna. It is independent on the weather conditions, independent on the sensor, and independent on the processing schemes. The cons are that it is a limb sounding technique, and the horizontal resolution is relatively low, which is about between 70 to 250 kilometers, and it needs model for retrieving temperature, pressure, and water vapor. So the methodology that we have used for analyzing the extreme events is this. We interpolated the profile measurements with a common vertical resolution of 100 meters. This is needed because the vertical acquisitions are not constant with different satellites. Then we geolocated all the profiles, and we indexed them with respect to the mean tangent point with 5 degrees resolution. We did sampling. The final reference climatology was sampled at 1 degree latitude longitude. Then we averaged all the values at the same altitude, obtaining one reference profile for every latitude and longitude. And finally, we computed the anomaly, which is a percentage anomaly profile for each parameters. And this is needed for understanding what is the contribution of the extreme event in comparison to the standard atmosphere. One of the example is the study of convective systems. This is one of these convective systems that we have analyzed. It was a squall line in the Pacific Ocean, and you see the black line here is the GPS radio occultation, and the white line is the Calypso track. So what we did was to compare the Calypso cloud, the Calypso attenuated backscatter on the cloud, and we compared the profiles from the GPS radio occultations. We show here the bending angle anomaly of this radio occultation, and we see that there is an increase of the anomaly corresponding to the cloud top from Calypso, and then here the temperature profile. And from the temperature profile we see that there is a coldest point just corresponding to the anomaly bending angle and to the top of the cloud. So according to this, let's just go back. According to this, we assume that the cloud top, even for the convective systems, is usually where we have this bending anomaly spike. And with the same technique, we have also analyzed the thermal structure of the convective systems, and this is what we got analyzing few hundred convective systems temperature profiles. Then comparing the cloud top altitude from GPS radio occultations according to the technique that I explained it before with the bending angle anomaly to the cloud top from Calypso for about between 50 and 60 convective systems, we got this scatter plot, and we had a correlation of 0.93 and root mean square error of about 100 meters. We did the same for tropical cyclones. This is the scatter plot, and we compared the cloud top of the tropical cyclones with the cloud top from Calliope. We got a correlation of 0.98 and the root mean square error of 365 meters. And we also characterized the ocean basin, the tropical cyclones for each ocean basins, and we have seen that in the southern hemisphere, South Pacific and South Indian here, we have the highest tropical cyclones, and we reached the coldest cloud tops. We also used the same technique for detecting possible overshootings, and here you see the tropopause altitude at different latitudes, tropical latitudes 20, 30, 30, 40, and the shaded area is tropopause plus and minus standard deviation, and all the dots are the cloud tops that we computed using GPS radio occultations. So all the dots, green dots are supposed to be overshootings, the purple ones are probably overshooting, and the blue ones are not overshootings. So with this technique we can also do it, and this is the map of overshootings compared to the map of the collocation between GPS radio occultation and tropical cyclones. We finally have used the same technique for detecting the volcanic cloud tops and for analyzing the influence of the volcanic clouds on the stratospheric temperature. So we have analyzed 3 different eruptions, Nabro and Puye, because they were the largest eruptions, and so we had the opportunity to get a lot of collocations with the GPS radio occultations, and Eyjafjall. But unfortunately, since it was not that large, we didn't get so many collocations. So in case of Nabro, we got 240 and something collocations, for Puye more than 1,000, and for Eyjafjall just 13. So here I show the tropopauses with the horizontal lines for each eruption, and the cloud top computed with the bending angle anomaly technique. Then I also compared the cloud top with the bending angle technique with Calypso, as I did for tropical cyclones and convective systems, but I could do that just for Nabro and Puye, and this is the scatter plot. In this case, we have a correlation of 0.94 for a total of 10 cases, and root mean square error of 930 meters. Finally, an analysis of Nabro eruption. Those are the collocated profiles on the same area of Nabro before the Nabro eruption, and the black line is the average of all those profiles between the 1st and 11th of June. The eruption was the 12th. So you see that this is the trend of the profiles, and then here in exactly in the same area for the following days and following the eruption from the 12th to the 15th. So we see that in the upper troposphere, lower stratosphere, the profile is completely opposite. It was there was a cooling before the eruption, and it was warming after the eruption. And this warming here stood there for a long time, because this is the profile in May, June, July, August, September, October, and so on. So you see that before the eruption, this was the profile. After the eruption, we had the warming just above the tropopause, which stood there for at least 5 months. So this means that the eruption directly reached the stratosphere, and this is an example from GPS radio occultation. And yeah, that's it.
Thank you again. And time for one short question. Yeah, please.
Sorry, I can't hear you. Yeah, so I have used for SO2 the NASA measures OMI datasets, and for ASH the Clarice algorithm. So this was my proxy for detecting the cloud, and then I collocated the radio occultations on those clouds.